heart rate? It decreases heart rate. Okay. What's the effect of acetylcholine on stroke volume?
Increases.
Tricky question. So what I want you to do is answer directly, not down the line. If it does this, and this happens, and this happens, and this happens. So acetylcholine, remember stroke volume has to do with contractility. Increased venous return is going to increase stroke volume because we're stretching the vessels, the walls more, and there's a greater force of contraction from Starling's law, called the preload effect. But however, acetylcholine doesn't have any receptors on the ventricular wall. So acetylcholine may change venous return. Acetylcholine will increase venous return because it's increasing ventricular filling time. But if I ask you what's the effect of acetylcholine on contractility, on stroke volume, it doesn't have any direct effect. So I don't want you to think, okay, if it does this, then this is going to happen, then this is going to happen. But answer for the direct effect. And acetylcholine is not going to change directly the contractility of the ventricles. It has no receptors. Okay? Yes, you can argue, well, it made the heart slower, therefore it filled up with blood more, therefore it contracted harder. But as far as the table is concerned, there is no direct connection between acetylcholine and the heart beating harder because there's no receptor for acetylcholine on those ventricles. So that's part of what I want to go over with you tomorrow. Okay? So that there's not a confusion on that aspect. Okay? So slowing the heart rate is going to increase venous return. Exercise. Why does exercise increase venous return? Remember, the skeletal muscles are sometimes called another pump because on the deep veins, as you contract your skeletal muscles, they get shorter and fatter, and they squeeze the veins, which melts the blood up past the valves. And so exercise, squeezing the veins, is going to cause more return. Remember, the veins are our volume reservoir, and so we're increasing that component. Same with intrathoracic pressure. It's going to squeeze more blood into the heart. Okay, I don't want to talk about that yet. Okay, so ions. Let's go back to this slide here for potassium. If we look at the contractile cell, and you probably covered this in Bio 430 when you were talking about the effect of ions on nerve conduction. Here's the plasma membrane. There's more potassium inside the cell than outside the cell, right? Potassium is an intracellular ion. So, I'm just going to do blue. All right. So these are potassium ions. They are in higher concentration inside the cell than they are outside the cell. So when we open a potassium leak channel, whether we do so have them there all the time or whether we do it with acetylcholine opening a potassium channel, the direction of diffusion is going to be down the gradient outside the cell. I think you're pretty comfortable with that. Now, if we go into hyperkalemia and we add more potassiums outside the cell, two things. Gradient is not as steep, so the rate of movement is going to decrease. All right, if I have a marble on a board and the board's flat, it's not going to roll, or my pen's not going to roll off the desk as fast as if I tilt the desk. The other thing is the positive ions are going to have a opposing effect polarity, like positive propels or rejects the other positive ions. So between those two, less potassium ions are going to leave the cell. That makes the inside of the cell more positive. And that's what we see up here. The dotted line represents the increased positive charges inside the contractile cell if we have a lot of potassium outside in the connective tissue. So that increases the excitability. How does that get to a slower, weaker contraction of the ventricles?
I just wondering, it looks like it peaks out about the same, but it doesn't drop as far.
Yes.
So,
That's what I discussed here. So the higher resting membrane potential, more positive resting membrane potential, means that some of our sodium ion channels are going to be activated early. They're going to reach the threshold of a few of our sodium ion channels. Okay? They're going to go into refractory period and not be activated as we reach threshold with the rest of our normal action potential. The other is, notice how short this depolarization is. Current is dependent on remember, electrical current is the flow of charged particles. Again, if I have 100 charged particles here and none here, the current's going to flow faster than if I have 100 here and 90 here. So the difference between this current and this current is much greater than the difference between this current and this current. So as we move the inside of the cell more positive, when we get to like 8 milliequivalents and 9 milliequivalents, the current that is created when the action potential voltage-gated channels for sodium finally open is so little that it takes longer to travel from this cardiac cell to this cardiac cell. So conductance is slowed, the QRS is spread apart, and the force of contraction is not as much because we have a change in the amount of calcium as well as sodium changes. And so we go from this to almost, we lose our P wave, and we go to almost a sinusoidal, very slow wave, and the next thing after this is fibrillation and death. So it has to do with affecting, you would think, oh, it's just going to depolarize easier. But it actually affects how fast that conduction occurs through the ventricles. So it slows that down, spreads it out, heart rate then gets slower and weaker as calcium levels are affected as well. So that's the extent down here. A decrease in inward sodium current slows impulse conduction and prolongs the membrane depolarization. It takes longer for the whole ventricle to contract. Okay. So that essentially, I know there's a lot of words on there, but that essentially is what I want you to understand, is that the inside of the cell becoming more positive, there's not as much difference in the current, then has a lower gradient and doesn't travel as fast. I'll go over those tomorrow. All right, so when we look at the second thing now, so we've looked at cardiac output via stroke volume and heart rate. So increasing heart rate and or increasing the stroke volume is going to increase the overall amount of blood that we put into a blood vessel. That's going to increase blood pressure. Then the next thing that we look at is peripheral resistance. Often I'm going to come back to this one. You have that chart, but you don't have the arrows on it. So peripheral resistance was our second component of blood pressure. Peripheral resistance is the force that the blood flow has to overcome to move down the blood vessel. So cardiac output is affecting this pressure against the vessel wall. Peripheral resistance is affecting this pressure coming behind it that has to push it through. All right? So the three factors are the diameter of the blood vessel, obviously we see this with airflow. So if you were to try to breathe through 10 small tubes rather than one large tube, it's going to be more difficult even though the volume is the same because the air particles are bouncing along the vessel wall. So if we have a large vessel carrying the same volume as several smaller ones, this is going to have greater peripheral resistance because more of the blood is going to be in turbulence against the side of the vessel wall. Because we have water molecules, we have dissolved proteins, we have blood cells. In the larger one, a greater proportion of that blood is in laminar flow and is not going to be involved in the turbulence against the blood vessel wall. Okay? Cutting a blood vessel diameter in half increases the peripheral resistance by 4.
You know, I tried doing that on that experiment to the 4th power. I couldn't get the numbers to come out
Pick
the
them out
same.
the same.
It was close, but not quite.
Software problem. The length of the blood vessel. Obviously, if the blood only has to travel this far, it's not going to meet as much resistance as if it has to travel 5 times as far. As we were, you know, it's a little difficult to change the length of your blood vessels. You can't do it overnight.
Really?
By increasing adipose tissue or muscle tissue, you can add to it. By decreasing it, you can remove it. But again, unless you cut a leg off, you can't do it rapidly. Viscosity refers to blood thickness. So Lance Armstrong has been in the news off and on, all right, with the blood doping and the testosterone use. Blood doping essentially, if you do it with your own blood, means taking out your blood over a period of time and spinning it down so you have just the packed red blood cells. That's what's transporting the oxygen. And then prior to an athletic competitive event, injecting that back into your body so you have twice as many red blood cells to carry the oxygen. But it also is thicker. You have a greater proportion of cells. Your hematocrit would be higher. And the heart has a greater amount of work to pump thicker blood. So it's kind of thinking of it in viscosity. You're making bean soup and you have 5 cups of cooked beans and 10 cups of broth. You put in your blender versus 5 cups of cooked beans and half a cup of broth. You're going to have, it's going to flow less easily with the thicker soup. And the heart has to do more work to push the solid cells and dissolved proteins through the vessels. Okay? So anything that changes either the number of cells or the amount of fluid in the body is going to change viscosity.
Will aspirin change blood viscosity?
What aspirin does, when we talk about thinning the blood, it doesn't really change viscosity. What aspirin does is it affects, remember thromboxane was one of the eicosanoid types? So aspirin prevents thromboxane synthesis. So in other words, platelets don't become sticky. So it's not so much that it changes the actual number of cells or amount of fluid as it decreases the likelihood that the platelets will settle out and start sticking to each other. So it's a kind of a weird use of the term to thin the blood. So my husband lives in Colorado now. At a higher altitude, your kidneys stimulate the release of erythropoietin, and he should have a higher hematocrit. Men do have a higher hematocrit, more red blood cells than women do anyway because of their muscle mass, all right? And at an altitude of a little over 5,000, his apartment's on the 21st floor, so a little bit more than that.
21st floor.
He's going to have more blood cells per mil than he would if he was still living here in Sacramento, which is what, 16 feet above sea level or something like that. So again, dehydration, all right, or overhydration will also affect viscosity. Now, again, when we start talking about hydration, we're talking about overall blood volume. So if we have more blood volume, we have what happens to venous return. So there's a point here